Should I start? All right. So let's continue. Good morning, everyone. So I got a couple of questions after the talk yesterday, and I thought I could make a comment for everyone. So I took note of the 3 comments. So the first comment that I've been asked a number of times was about the positivity of this quantity, because I was not using the optical theorem here. And I say it by words during the lecture because of a question by Michele, but let me say it again more slowly. So the kernel, which I'm not going to write down again, but you have it in the notes, and I wrote it yesterday, you can just check it explicitly positive throughout the whole range. So now we are left to talk about this discontinuity. And now for the discontinuity, note that I was considering t. So in particular, for the derivatives, I was taking t equal 4/3 of m squared. All right. And now it's a very simple exercise to write. Now, what was the idea? The idea is write. Let me write it like this: t of z. Okay. Write that's going to some constant, but write the amplitude in terms of the Legendre and the partial waves. All right. So the imaginary, and we want to go to t equal to 4/3, right? So let me remind you that cosinus, so remind that is equal of cosine of theta, okay? And now use the Mandelstam variables definition to check that cosinus of theta is 1 plus 8 over 3 times s minus 4 at t equal 4/3, all right? So now you need to plug this inside here, okay? And what, is it clear what I'm saying? So, yes, all right. But then you see, now take the imaginary part of this, okay? Now, the discontinuity of the partial wave is positive by unitarity. Remember, I showed you, we were seeing that the partial waves obey a unitarity equation with a cut that starts at 4m squared, okay? So now we are left to check whether these guys are positive, but the point is that this constant, this function, 1 plus 8 over 3 over s minus 4, is larger than 1 for all s larger than 4, okay? Right? So in the whole interaction domain, we are evaluating P of L at z larger than 1. That's the conclusion from this equation, okay? And now if you remember the PLs of z are functions that look like so. For various L's, they oscillate around the interval, but they shoot off to positive values at z larger than 1, okay? And this is true for any L, okay? So we are evaluating the Legendre polynomials at values which are explicitly positive, okay? That's why we could use that this is positive, okay? Clear, the statement? We are evaluating all the Legendres in this region, okay? When we take 4/3 on T. Now, the second question I was asked, which I realized that perhaps this was not obvious to everyone, was about, so, the second question I was asked is, well, I was asked first about real analyticity, and this was the statement that the function below the cuts is real, okay? So we had this idea. We would like to do an analytical continuation that satisfies this equation. all right? Because for real s, we would like the function to be real, okay? But now you see, we're getting discontinuities because we are doing an equation like this. We are doing, when we are doing the contour, we are evaluating the function right above the cut and right below the cut, right? So, and then we take the difference between one and the other. So we have fs of I epsilon minus m of s minus I epsilon, which is nothing, of course, that m of s plus I epsilon minus m of s plus I epsilon start, okay? So that's why we write and this is nothing but the imaginary part of the function, right? The value of the function minus its complex conjugate. That's why we write this continuity in terms of the imaginary part. I imagine that for half of you was obvious, for half of you not, if you have not been exposed before. So I wanted to clear up these basic things before we move to more advanced things. The last comment that I was asked by some of you was about the contours and about the matching to Wilson coefficients. Now, throughout these lectures, I have been trying to be very explicit in differentiating when we make assumptions about effective field theory and when we are making assumptions only about the analyticity of the amplitude. Okay. Now, this equation over here, or these equations over here, they do not incorporate any statement about effective field theory yet. Okay. So the statement about effective field theory, it's an assumption that we need to add when we want to compute these coefficients in a quantum field theory, a weakly coupled quantum field theory, right? And here, why did I change the contour? In principle, we could use also the same contour I was using to derive. So this is called the fixed T dispersion relation, okay? And for this dispersion relation, I used a contour that was going all throughout the upper and lower half plane, right? Here I draw this other contour, but actually is the same, okay? The contour. The only, because, let me see how I can say it very quickly, but the point is that to derive this equation from here to here, so what we are using crossing plus this real analyticity condition, all right? Okay, which we can combine them into a now we can combine both equations into a single one, okay? I'm starting to make a mess in this blackboard, so let me write it elsewhere. To derive this equation, to go from here to here, we are using crossing plus real analyticity, okay, which we can combine into m of minus s star equal of m of s star, okay? So this last equation, what it does is that it maps points in the upper half plane to points in the upper half plane, okay? All right? So, so actually, the only difference is that when I was using the other contour, I used this equation after doing the derivation. When I was reducing the whole, I used the I use this equation in some intermediate steps when I managed to write the whole dispersion relation in terms of an integral on the unitarity cut, okay? While when I'm writing that contour, I'm using this equation from the beginning, but actually it's the same, okay? So there is no difference between contours. The only difference, if you wish, is that here I wrote it explicitly from 4m squared, okay? That's the only substantial difference, while here I'm writing an S naught, okay? That's just a choice that we made to put ourselves in a situation of using this as node as a sliding scale for the effective field theory evaluation. Okay? So that's the only difference. And this we could have done it also for the other dispersion relation. Okay? Okay? Let me see if there's any other preparatory comment I wanted to say. No. So let me leave these equations here, which I will comment on. I will comment on these equations later on. Okay? Now let's continue with the derivations about crossing symmetry. So I remind you that we are trying to. Any question about the preliminary comments? Or all right. So I remind you that we managed to write this dispersion relation that was explicitly symmetric between S and U exchange. All right. And we exploited the positivity of this discontinuity to put bounds already in some Wilson coefficients, right? So in particular, well, we derived that C2 was positive and that C3 was bounded by C2, right? So we wrote an equation that looked like C2 C3, we wrote C3 smaller than 9/8 C2, and I claim that it's larger also than some value, and we wrote that C2 was positive, okay? And let me quote for yesterday that C0 was equal to some non-positive constant, MT, plus some dispersive integral, okay? I will talk about this later on, all right? So for the time being, I would like to discuss this bound, and this will allow me to introduce a number of interesting comments that actually are more general than this example, okay? Now, so basically, we would like to impose this. All right. And then let me remind you another comment I made yesterday, which is that when we compute we can keep computing coefficients here by taking derivatives of the EFT coefficients in the EFT, and the first coefficient for which, so for C2 and for C3, we also have various options. We can take derivatives of S or derivatives of T to land into the same coefficient, all right? But it turns out that doesn't lead to any constraint on the system, okay? The first non-trivial constraint is for C4. Namely, we can compute C4 as 4 derivatives of ST or 2 derivatives of S and 2 derivatives of T, okay? And turns out that if you plug these equations, if you take these derivatives into this dispersion relation, it leads to non-trivial constraint for the partial waves, okay? And now we would like to exploit this more generally. Yes? This statement here? Okay, thank you. No. Okay, this is because we should remind ourselves that a prediction of crossing, we'll see why this follows from this equation, but a simpler way to see it is that from the effective field theory, okay, the amplitude, it admits an expansion where we're going to get like minus C naught plus C2 A squared plus T squared plus U squared, some C3 coefficient, STU, and you see, now I'm talking about C4. So C4, we can write it, for instance, as a squared plus t squared plus u squared. Needless to say, the number in here is about the degree of the polynomial, no? On the Mandelstam. So C4, which is this object here, right? You can extract it, and I'm defining C4, say as the derivative, let's say the fourth derivative on S of MST, say at the crossing symmetric point, just at some point in the okay, S equal T equal 4/3, right? But clearly, you can also obtain it from derivatives of T, right? And this is obvious in the EFT. It's just not it doesn't look like a constraint, right? But it imposes a constraint when you apply it on the right-hand side of the dispersion relation. What do you mean? You mean no, because wait. First of all, I was not careful here about some constant here, but I still think this is actually true. And you need to be careful of putting u equal 4 minus s minus t to the derivative. And then I believe you get exactly 1 on both sides. Okay? But even if we may normalize things slightly different, say you don't take this operator, but you take one which is slightly different, okay? This doesn't change the conceptual thing that we may obtain the coefficient C4 by acting on with different types of derivatives. That's the main point I'm conveying. I think you were forgetting to change u, right? Or not? You. Let me check it later. I think I'm quite sure I was getting it correct, the numbers. Okay. Let me check it back later, but I think it's fine like this. But the important point is that we want to build crossing symmetry now on the dispersive representation of the integral. Okay. Now, how are we going to do this? So we would like to. Now, of course, this what I'm saying here. What I'm saying here, this is for the lowest Wilson coefficient, but of course now we are just opening up an infinite set of constraints because arbitrary now degree polynomials of the Mandelstam are going to satisfy also these kind of constraints. Okay. These are often called in the literature null constraints. Okay. Now, how are we going to find all such null constraints or crossing constraints? So now let's be a bit more systematic. So what is the idea? The idea is take this equation here, all right? And decompose into partial waves. So you will get take this equation here, okay? And plug it on the right-hand side of this dispersive integral, okay? And let me be schematic, and then you can check the notes, all the details, but you will get mz of zt times k of z st t naught, all right? Plus mz of z t naught. 1 second. Yeah. K z of t naught s naught. Z t naught, right? Minus m z u k z s u t naught minus mz z t naught k of z u t naught s naught. Actually, note that because this was a SU symmetric, I may do TS symmetry or TU symmetry. Okay, that should be equivalent. Okay, so actually in this equation here I'm using TU symmetry. Okay, and now this is a functional identity, and this should be 0. Okay, and now comes the second step. Okay, and in the second step, well, so here we only plug in the dispersion relation. The next step is we decompose all this into partial waves. Okay? What do we get? We get 4 m squared to infinity dz sum from L equal to infinity to L plus 1 im of L of z and a kernel zt t naught s naught equals 0. Now the kernel, I'm not going to write it down now in full detail, okay? But maybe I can make some comments. But I hope it's clear how the kernel arises. No? You should just take this equation and integrate against the Legendre, right? So basically this FL is simply a linear combination of this case multiplied by Legendres. Simple thing, right? And now comes the last thing I wanted to write. Okay? Because now we would like to extract from this equation finally many constraints. Okay? This is simply a statement of crossing in partial waves. How are we going to do it? We can act on derivatives on this equation, the same trick we're doing for the EFT. Okay? So by acting on derivatives, let me define this Carly F of LK. Okay? Which I define as 4m squared to infinity dz from L equal to infinity. So the fact that we start with a L equal 2, it's because we had this number of subtractions, okay, that it's killing there is no contribution here, okay, from the spin 0, which is this contribution over here, the one that doesn't depend on t, okay. When you project this into partial waves, this ticks into the 0 partial waves, okay, but it does not tick when you take the differences, okay. And here I get im m of L of z, f lk L of z equals 0. And now this is a nice equation where here fl of lk of z is simply equal to L derivatives of s, so L derivatives of s, k derivatives of t, acting on the kernel, okay? Z s t, 4/3, and s equal t equal 4/3, okay? So these are all the crossing constraints, okay? And they're infinitely many, which now I'm labeling with 2 integers, okay? Any question about the logic? Yes? Thank you for the question. Okay, so it's okay to be confused because there are three Fs, no? But you know, okay. So this one, are you okay with this one? So let me repeat. This one comes simply from the Legendre projection of these kernels on the previous equation. Simple thing. It depends on one integer, which is the Legendre, right? Now we take this equation, and I define it, and we act with derivatives, okay? L derivatives on S, K derivatives on S, on T. Of the no, this is derivatives of this whole thing over here, right? This curly is simply derivative of this whole thing over here, right? It's maybe we don't need to define this, but let me keep it here. And now this one here, the non-curly, is this kernel on which I'm acting with the derivatives, okay? So the derivatives do not act on this, right? This is just the dummy integral variable. All the S antidependents are here, and that's what I'm defining here, okay? Which is the derivatives of this F in terms of T and S. Yes? Thank you for the question. Okay, so now let me provide an example, which is going to be precisely this bound over here, okay? Which now we can formalize. So example of how to use these constraints. Example. Okay? Now these constraints are, will not allow us to constrain C3 by itself, but only ratios of C3 over C2. So what we're going to ask now is, find for the minimum, let me formalize like this, of C3, okay? Let's say barring the im of FL, okay? Subject to, and now I put the constraints, C2 equal 1, curly F of LK equals 0, and im of FL of S larger than 0 for physical energies. Okay? So these are all the constraints. Okay? So this sets up some normalization on the EFT. Okay? These are the crossing constraints I just derived, and this is unitarity. Okay? And implicitly, there is, of course, built-in analyticity, because this is, let me number this equation. We may call this 1. IMFL in 1, okay? Or let me, yeah. Or actually, better way to write it is like as follows. Let's write the dispersion relation for C3, and let me call 1. So I recall you that we had C3 was M6 over pi, an integral from 4 to infinity, dz of 3 mz, z 4/3. There was a kernel, z minus 4/3 to the 4th, minus dt mzt of z minus 4/3 to the cube. And okay, for completeness, C2 was M4 over pi from 4 to infinity, dz z 4/3 over z minus 4/3 to the cube, which was positive, all right? So in fact, let me call this the equation 1, if you wish, okay? In 1, okay? Well, of course I mean 1 projected into partial waves, okay? Because I'm talking about FLs, okay? Okay, so now that's the problem that we need to solve. Okay, and framing like this, it may be not automatically obvious how are you going to solve it. Let me say here that this LK we're going to cut, right? We're not going to be able to put, and I want to put this in a computer, let's say, or in a bit of paper. And there are still infinitely many constraints, so we may just cut this constraint and look for some convergence as we increase the constraints, okay? Now, this problem allows me to introduce something that perhaps will be useful later, which is the idea of primal versus dual optimization. So here, let's say we are imagining that, so let's say this is a C3, okay? All right? And we are trying to minimize it, no? This is a C3 min. All right? So there are two equivalent ways to see the problem. One way is we explore in the space of allowed S matrices, allowed values for the evals. We vary inside that space, okay? And we look for the allowed value that achieves the minimal value of C3, okay? That's one way of seeing it. The other way, so this would be like primal. The other point of view on the optimization problem, let's call this C3 max, is the other way around. We propose values of evals which clearly violate, which are not allowed. They are not feasible. Namely, they cannot satisfy the constraints. Okay? And then we keep maximizing on this space by excluding values of C3 that cannot be achieved. Okay? So let me write it in a more clear way what I mean. Okay? So this optimization problem, the way you can think about it is like any optimization problem, you write a Lagrangian, which can depend on some variables m and some Lagrange multipliers. Okay? And in this Lagrangian, we're going to have some optimization goal, okay, which I'm calling O, okay, plus some constraints on our variables m dot lambda, okay. So think of the optimization goal as C3, okay. Think of m as our variables in the S matrix, namely the values of evals, okay. Sorry, think of m as all these constraints here. So constraints on the values of the S matrix, and these are simply some Lagrange multipliers that impose these constraints on m. Okay. Now on this Lagrangian, if I iterate out the Lagrange multipliers, right, I'll end up on this problem, right? Because I will be minimizing subject to these constraints. Okay. But now the idea of the dual optimization problem is to do the other way around. Now we're going to iterate out first the primal variables, okay, and then look for optimization. So in equations, this looks like so. So we define what is called the dual function, which depends on the Lagrange multipliers. Let me define it here. D lambda is equal to the minimum inf, okay, of the Lagrangian. Okay, this is the definition. I define the dual functional, which depends now on the Lagrange multipliers, by extremizing over the variables m. Okay. Again, think of m as basically as the partial waves in our problem. Okay. that appear in the constraints. Okay. Okay. So now we have this set of simple equations, which is that d lambda, d of lambda, okay, d is called the dual functional. It is more or equal than the supremum of d of lambda. Okay. This cannot be more obvious. Okay. But now comes the trick. Okay. Let me call it, which is this was defined as inf of L. Okay. Well, let me write first one intermediate equation. Let me write this as sub of lambda inf of m L of m lambda. Okay, that's just a definition. And now there's a theorem called min-max theorem, which comes from set theory, which allows us to exchange supremum and infimum here at the expense of an inequality. Okay? And now inf of m, supremum of lambda of L of m lambda. Okay? So this comes from a min-max theorem, which I'm just quoting here, which allows us to exchange supremum and infimum. And this is more or equal to O star. And by O star, I mean the optimal value of our objective, the objective that we're trying to optimize. Okay. Now this is a tricky. This is where the meat is. Okay. And why does this inequality follow? Note that here we're doing the supremum of the Lagrangian varying lambda. Okay. But you see, if I'm varying lambda in the Lagrangian, this should off to infinity, right? I can just take lambda to infinity, right? Except if the constraint is satisfied, in which case I will get O on the Lagrangian. And now I take the minimum value while I vary the constraints. So this will provide for me O star. Should I repeat the logic? Yes? Okay. So I'm taking supremum of lambda, okay? Supremum of the Lagrangian by varying lambda. Okay? Clearly, I can just send all the Lagrangian multipliers to infinity, okay? So this guy just shoots off to infinity, except if I'm taking values of the S matrix that are feasible, namely if the constraint is satisfied. If the constraint is satisfied, this goes to 0, right? Okay? In which case the Lagrangian is O. Okay? And now I repeat this exercise by also scanning in M, in the allowed values of the S matrix that satisfy the constraint. So this is going to provide for me an optimal objective. It's clear? But you see, now this is a powerful equation because it means that if I write a Lagrangian for this optimization problem and I first iterate out over the constraints instead of iterating over the Lagrangian multipliers, I will end up with this so-called dual functional. And now what's the rule of the game? I take the dual functional and I maximize that one, and I will converge from below to the C3 minima. And not only that, because of this inequality, okay, any evaluation of the dual functional provides a true bound to the problem. Okay, even if I don't manage to be optimal in this in looking for the minimal value of this object here, okay, any evaluation of d of lambda will be just below the optimal objective, okay, or star, okay. So I thought it was nice to mention this in the context of this problem because now it's clear what we are going to do. We're going to write a Lagrangian for this equation, iterate out over the primal variables, and then we end up with a simple functional which we need to maximize, okay, to get into the minimal value of C3, okay? So now, instead of minimizing C3, we maximize something else that conveys from below to the C3, okay? Now, what is the dual functional? I'm not sure it's in my notes. Is it in my notes? Okay. Actually, this problem is linear, so it's straightforward to write the dual equation. And now, maybe, let me call this as the primal problem. And now there is equivalent dual problem, which I'll write here. And that's the one that we're going to solve, actually. And now this one looks like max of minus lambda 2 where I need to vary lambda 2 and nu n comma m, okay? Subject to, let me write it down and then I explain. Subject to minus 1 lambda 2 of KL2 of S plus KL3 of S plus sum over nu m FL of n comma m of S larger than 0. And now this becomes something quite simple to put in a computer, okay? Let me tell you what is KL. So here, KL2 and KL3 are nothing but the kernels that appear here when we project two partial waves. The one for C3 and the one for C2, okay? I may write them. So, okay, I can write it, but let me write the one for KL2 and only schematically the one for KL3, okay? And then you can look for the nodes. And then the one for KL3 of S is equal to 48 PL 1 plus 8 over 3 S minus 4 over S minus 4 thirds to the 4 plus some other piece, okay? This first piece I wrote is the one that comes from the first piece over here into the partial waves, okay? And remember, it's important, these FL and M's are simply derivatives, okay, of this kernel, okay, evaluated at the crossing symmetric point, okay? Sorry, not the, sorry? That's the nice thing. Lambda 2 and mu n are the Lagrange multipliers, so maybe I can write an intermediate step, okay? But one comment, if you take this problem now at face value, okay, now you can just put it in the computer, right? Because this constraint is totally explicit, okay? I'm giving you the exact kernels, okay? Okay. And 1 second, sorry, here I made a typo, apologies. Sum of n, m, nu, n, m, okay? Now, lambda 2 and nu and m, I'm going to show you now, are simply the Lagrange multipliers on the original problem, okay? But now you see, what we are doing is we are barring over all the Lagrange multipliers, okay? And maximizing in order to approach from above the value of C3, okay? So now you can just put this into computer because I'm giving you all the kernels, okay? And what is left, lambda 2 and nu and m, are simply dummy variables over which you vary, okay? Now, how do they arise? So you write a Lagrangian, like so. So you will write C3, which is what we are maximizing, or sorry, minimizing in the primal, okay? Which is simply this function over here, f else. Let me write this schematic, f else, okay? And let me write as f else, okay? Of f else, okay? Plus, and let me write this problem as a function of f else and lambdas, okay? The Lagrangian, where lambdas, okay, it's a lambda here, it's a short notation for lambda 2 and nu and m's, okay? And f else is my primal variables. Lambda is my Lagrange multipliers, okay? So I have the Lagrangian is equal to C3 of FL, okay? And now I need to impose the rest of the constraints, which are written over there, okay? So I will write C2 of FL, okay, minus 1 times lambda 2, that would be one constraint. And note that C2 of FL, you should be plugging this equation in partial waves, okay? You should be plugging it here, okay? And now we continue, plus, what is it? FL case. So now you write F L case, new L case. And this again is there's FL case, where is it? It was defined before, the FL case. It's defined here, thank you. It's also a function of FLs. And I'm writing here a new LK, okay? And now you should plug the definition of C2, the definition of C3, and the definition of FLK, okay? It's a linear problem, so it's very simple to differentiate over FL, and you're only going to be left with the kernels, okay? Which is why we'll end up with this constraint on the kernels, okay? Modulo these Lagrange multipliers that appear on the constraint, okay? And now, okay, it's clear how you would put, now it's pretty explicit, no? That we know how to put this. So what we have achieved is that in the original problem, the primal one, in order to find the minimal value, would be forced to explore in the space of FLs, okay? This is something that we could do, and we'll do it later on in the course, but this would require us making some ansatz for these functions. And here we're skipping these ansatz by going into this dual optimization, and then we are left with this simple kernel here, okay? Now, maybe I will include in the note a simple Mathematica file to solve this problem. It's 5 lines, okay? And then I can tell you what you get. So what do you get? So for instance, if you only take the one constraint, so you could take one constraint, namely one new, say 1, 3, okay? You take one constraint, then, well, I didn't quote it here in my notes. Well, let me quote the final number. The final number, if you take a few constraints, or there are 5 or 7 constraints, you already converge pretty well to the final number, which is 2.250, okay, here. All right. Now, Okay. So maybe I can make a small recap of where we are and where we are going. Yes? Um, yes. The one I'm quoting here is optimal to the extent that you only look at the two-to-two scattering. Okay? So even though, yeah, that's the statement. Because it's an open problem which is really hard to solve because yeah, we don't we so it's not clear what are the constraints that looking at higher point matrix elements are going to give, because in principle those can be very small, especially at low energies, and this constraint is mostly affected by parts of the dispersion relation, because you see these kernels fall off at infinity pretty fast. So I think the fact that it's optimal within the 2-to-2 sector means that we can, if there is any further constraint from multi-particle production that we ever manage to include, it will be negligible in principle because of this fall off of the kernel. Yes? Yeah. I'm doing a bound. Yeah, that's something I would like to address next, actually, which is the fact that, so using positivity, you see, so far we have been using a linearized version of unitarity, okay? Positivity of the imaginary part of the amplitude, okay? And when we include this crossing constraint, the bounds become much more powerful, but still we cannot say anything about C3 by itself alone. We are only accessing ratios of C3 over C2, okay? Now, I would like to, this is especially one of the next things I would like to discuss is, this is the kind of ratios that you care when you are in effective field theory. But now we may ask other types of questions, like, for instance, what happens if we have theories that are strongly coupled all the way to 4m squared? And now we would like to obtain bounds on C3 that do not depend on C2, but are simply normalized in terms of the mass of your scattering particle. Okay? So some absolute bound on C3 in units of the mass. And those are possible. That's the topic of the next discussion I would like to have. Okay? But thus far, indeed. I normalize it to 1, you can normalize it to whatever. The point is that we are only accessing so far to these ratios. Okay? Now, what do I have, 40 minutes? Yes? All right. So, any other question here? Okay, so now I would like to motivate the next subject, which is an introduction to the non-perturbative matrix bootstrap, or to the subject of obtaining bounds on amplitudes that are strongly coupled. Okay? By the way, let me mention that in the notes, but I'm not sure, I'm not going to have time to review it here, but you may read for fun. I include an example of a two-dimensional example of a theory for which we know the exactest matrix, okay? And then it's fun to play around and see how C2 comes out positive, and it's a theory for which we know you will have you will see full details in the notes, okay? So these a parenthesis. Now we are going to leave the topic of positivity, but let me mention that there in the example, there's a beautiful example in 2 dimensions, where here in the UV you have a supersymmetric theory, which looks like so. So there's a free fermion and a free boson. Okay? And now you consider, so you can turn on a potential and a Yukawa, say psi phi, okay? Actually, the normalization is something like this, psi bar phi, okay? And well, it turns out that this theory, okay? It turns out that this theory, what you can do now is perturb it in such a way, so this theory preserves supersymmetry. It's a supersymmetric theory, just because the way we have tuned the quartic and the Yukawa, okay? Now you can deform this theory, okay? You can deform this theory, okay? With a supersymmetric, with a supersymmetric relevant perturbation, which looks like so, phi square square, okay? And now this perturbation gives a non-zero value for the ground state of the theory, so it breaks spontaneous supersymmetry. So it gives a mass to the boson, but leaves the fermion massless. Okay? So this theory flows in the IR to a free fermion. Okay? You will see full details in the notes, but I found it a cute example which you may enter. It's a divertimento, okay? Out of the course, it's a divertimento where you flow to a free fermion, plus the way you arrive to the free fermion is with the relevant operators, no? So you will have d phi, okay? You will have a fourth fermion, okay? And now we can run all this machinery of dispersion relations for this S matrix. There's a coefficient here, there's a sign here, with C2 is positive, okay? Okay? Unsurprisingly, because now we have seen C2 positive in many ways. But the nice thing is that in this example, the S matrix is exactly known, and it takes this simple form. S of S is equal to S minus IM, S plus IM. Now, depending on the conventions, but in my conventions, it's better to put here a minus, let me think, no, like this, plus, okay? Like this. And you see, when you expand these at low energies, you get precisely the correct signs. And I just wanted to mention this because so far, all the examples that we know in higher dimensions, of course, they are not exact, but there are known examples which are exact, and then you get also, of course, what you expect, that C2 are positives, yes? I mean, one second. It's a good question, but it's not in the direction that you are saying. From the UV, it's very hard to guess that C2 is positive, right? Right? But you could ask your question is slightly different. You could say, in the IR, we know we have a Agostino. If you write the EFT of the Agostino, do you get automatically C2 positive? And the answer is yes. Namely, well, the answer is no, in the sense that no, you cannot guess purely from supersymmetry. Okay, it requires some mild assumptions still about having weakly coupled UV completions and okay. I mean, in principle, in the IR here you could take both signs, okay, and still be compatible with the linearly realized supersymmetry. Okay. This is just an aside comment as a divertimento that you may read in your free time. Okay. Now, let's go now to the non-perturbative S matrix bootstrap, and I would like to give a motivation via an example. Okay. Okay, so the example is here in a way. So I would like to discuss a simple avatar of a phenomena that we are already seeing here, okay? And then I will show you a solution for that problem. And the problem is that if we think of a theory that, so you see here, this is an example. So here, consider the amplitude, okay? And compute it in perturbation theory. You're going to get some logs, okay? And some calculable coefficients in front of the logs, okay? And now you can just compute these intervals on the amplitude, okay? So at tree level, as I told you, these various intervals just split for you the coefficients of the operators, no? But when we compute loops, we get these logs, okay? And these induce IR divergences that give you these powers of 1 over S, okay? So if we want to access a very high order dispersion relation, we lose positivity right away for the T-level Wilson coefficient, okay? Of course, if we are in perturbation theory, we don't care so much because we may just argue that these logs are just a small modification of positivity, okay? But it's actually lost by a calculable effect, okay? Within perturbation theory. So let me make it more clear even. So A2, sorry, A0, let me write better. With loops. A0, so A0 is C2 plus irrelevant contributions, namely contributions that go to 0 when you make S small. S is the sliding scale that I'm using for this interval, okay? Now, A1 is going to be C4 plus some logs, okay? I can write it exactly if I have it. Well, there's a coefficient here, of course, but I didn't write it in my notes. You can find, but I gave you the reference in my notes. There's some coefficients beta force, okay? Plus dot dot dot. So also this also blows, but in a lower pace than these power-like corrections, okay? So you see, at the moment that we turn on loops, we have these small corrections to the positivity statements. So this is a loop level. Tree level. So tree level will be simply A2 equals C2, A1 equals C4, and A2 equals C6, and so on, okay? So now we would like to go to another regime. So these are different types of theories. We like to go to a regime where we don't want to assume weak coupling below the scale lambda. We would like to be even more agnostic. We would like to allow for strong coupling all the way to here, okay? So different type of regime, but it could be interesting for certain types of theories. Yes? Yes, yes. Yes, yes. There's all sort of there's an interesting phenomenology about which type of particles you need to add in the scale lambda in order to achieve the runnings that you want. Okay, and of course, if you have a loop of fermions, they contribute negative to say quartic type couplings. That's true. But here I'm making a slightly more general comment, which applies not only to scalars, but it's really more general what I'm trying to say. What I'm trying to say is, so I'm working with the scalars here all the time for simplicity. I don't want to carry on all sorts of indices, okay? But the logic is the same. The logic here is that that if you're interested in theories that are strongly coupled, that there is no mass scale separation between the mass of the particle and some other EFT scale, okay, then these bounds start losing its power, you see? Because now you could be interested in physics. So here we do separation of scales because in a way physics is boring from here to here. Boring, I mean you do a trivial contribution and it captures what is going on, right? And then you ask about interesting physics, assuming that there is some potential strong coupling or lots of particles appearing at the cutoff lambda, okay? But now we would like to ask different question. We'd like to ask what happens if there is no separation of scales, and now we would like to take S here small, because interesting physics is happening already here, okay? And now you see that some of these bounds may lose its power because we're going to be dominated by these logs, which may not be small anymore, okay? Now I'm going to show you an even simpler problem where this effect is also present, okay? And we're going to still be able to bound this coefficient sharply, exactly, okay? Even when there is the presence of these guys, okay? Because, okay, I think it will come clear when I write the example, okay? It's clear where I'm going, more or less. So this is a parameter in your Lagrangian, right? So even if it is observable, it's contaminated by these IRFX, it presumably has some bound, right? We presumably cannot be arbitrarily large because of unitarity, but we could not access this bound by using this technique. We should now use something more powerful if we would like to bound these strongly coupled theories, okay? And this is the topic of the so-called non-perturbative S matrix bootstrap, okay? And I would like to discuss it in the context of an example, which will allow me to discuss also some interesting physics in passing by. So next, I would like to discuss as a toy model, but it's also a model that is relevant for real physics, which is a model of flux tubes. Okay. So you see the flux tubes. So now imagine a QQ bar pair. Okay. Okay, which is very heavy, okay? Much heavy, I mean, than the confining scale. And now you separate this QQ bar. You expect to generate some chromodynamic flux tube, okay? Which can be measured in the lattice, okay? Now, when this flux tube is large enough, we may forget about the boundary conditions, okay? And we are interested now on the dynamics of this object, okay? So think about, for instance, pure SUN, no? So the potential, okay, or the vacuum energy of this object, okay, grows linearly with the distance, okay? And then there are some small 1/r corrections, okay? I should put here an Elias -2, right? All right. So there is a linear growth, and there is some tension, okay, inverse tension, which Ls carries units of distance. So these are units of energy, okay? Now, what is the thing? We can describe this object, okay, by an action which is a now two-dimensional action, okay, because it depends on this object, okay? It breaks the bulk, the full bulk Poincaré is broken down to Poincaré in 2 dimensions, okay? And some rotational group around the string, okay, which is parameterized by orthogonal fluctuations to the flux tube. Okay. So now what we like to study are these small fluctuations on the flux tube. Okay. And in particular, we are going to be interested in two observables. One will be the potential energy between this QQ pair, or the vacuum energy of this long flux tube. Okay. Another object that we will be interested is in the scattering of these fluctuations. Okay. These fluctuations are often called Brannons, and these are simply the gallstones from the spontaneous symmetry breaking pattern between bulk Poincaré down to this product. Okay. So we may immediately write an action, which is the action of an effective string. Okay. So in leading order we have the Nambu-Goto, and this simply the induced metric, which we may write. Let me write it like this: determinant of d alpha x mu d beta x nu eta mu nu. Okay. And so it becomes much clearer if we work in the so-called unitary gauge. So this mu is an index that takes values on the so think about 4 dimensions. Okay. So this mu takes values in the 4-dimensional directions. Okay. And a way to write this is a nice. So this is a reparametrization invariant. But a way to expose the physical degrees of freedom is to take this gauge. So we take sigma alpha, comma xi, where I goes from 1 to d minus 2, okay? Which are the orthogonal fluctuations. And this depends on this sigma. And this sigma alpha, okay? So there are 2 coordinates here, and then d minus 2 coordinates here. So in total we have d coordinates, okay? So this is the action for the worksheet, okay, of this object. So, and now the higher orders on 1 over R can be captured. So the rule of the game now is to write any reparametrization invariant operator out of the metric. Okay, out of the metric or the extrinsic curvature. So we can write Ricci of H, right? Or so the extrinsic curvature kappa alpha beta is written as this. Let me write it better. Mu. Okay. Okay. So we can write kappa alpha beta, kappa alpha beta, mu. Okay. Plus, and now the next thing we can write down. Can I erase this to get more space? Or, well, I can write it. Let me write it smaller, okay? Plus R of H plus K squared. And now we have plus, say, G1 K4. So K plus G2 K. And there are various contractions that we can do. Mu nu or alpha beta, let's say square, okay? Or some other contraction, beta, gamma, sigma alpha, some other contraction, okay? They are 2 independent operators. Plus dot. Okay. Okay. Now, now there are two types of observables that we would like to compute. Okay. So let me discuss both of them. So one is the vacuum energy, okay, which is nothing but B times the effective potential, okay? And here the S matrix, okay? Okay. Now, let me mention very quickly what do we know about BF, okay? So BF of R, which by the way, maybe let me say one more comment here. So now, let me write it smaller because otherwise I'll not have time. So I will not have space. So now take the unitary gauge, okay? So you see, I goes from 1 to d minus 2, no? So if we're in 4 dimensions, these are the two orthogonal directions, no? The string can fluctuate in that direction or in that direction, okay? Now, when we go to the unitarity gauge, and now we go to unitarity gauge and we expand in a small derivatives, this action, okay? What do we get? We get something very simple. We get derivatives on our fields, right? The alpha xi, so kinetic term, right? Plus dot 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 that comes from expanding the metric, okay? But stuff with two derivatives, okay? So higher powers, but two derivatives here, okay? Now, this guy is a total derivative in 2 dimensions, the Ricci of H, okay? So it doesn't contribute on shell, okay? And this guy, it vanishes by equation of motion, okay? Because of these equations here, okay? So the first non-universal term that you can write down is this guy here, okay? So you see, no matter what is so this object is going to be generated in any confining gauge theory, okay? So take a pure Young-Mills. And for all such theories, the first term that depends on the details of the UV are these two operators, okay? This is often called a universality, okay? Namely that the first, that we don't get any corrections up to these 4 derivative terms. Sorry, 6, let me count, 8 derivatives, no? Because there are 8 derivatives, okay? Which you can read from there. There are 4 Ks and 2 derivatives, okay? So think of this action. I mean, you should not be too surprised from this action because we've seen the chiral Lagrangian, okay? And the logic is the same, no? If you wish, you can think of this, the induced metric, you should think of as the universal term that comes from symmetry breaking, no? Of the pion Lagrangian, right? It's just fixed by symmetries. Likewise, this is fixed by symmetries. And then we have the low energy constants, right? Which depend on the details of the UV, and we need to measure them. In the low energy constants, we write higher derivatives. So we write du, 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 right? This is the leading low energy constant, let's say L2, right? So these are analogous. This is the first term we can write down that doesn't depend, that depends on the details of the UV. That is not fixed purely from the symmetry breaking pattern. But you see, here we have way more universality than the pion Lagrangian, because the pion Lagrangian, the leading term is 4 derivatives, okay? While here the leading term is 8 derivatives. It's way softer, okay? So now, this is going to translate into the fact that when you look at the vacuum energy of the problem, or the S matrix, lots of low energy coefficients are only fixed by symmetry breaking pattern, okay? And we need to work more in order to see the first leading effects that depend on the details of the confining theory, okay? So let's compute BF just by power counting, okay? So first we get cosmological constant, right? I'm computing the effective potential for this theory here, okay? So first we get the cosmological constant, Ls minus 2, right? Right? Which has units of energy density, right? Ls has units of length, okay? Oh God. I have 5 more minutes to introduce the problem. Then we have the next correction, okay? Which comes from the kinetic term here. Okay. Here I should have Ls. I'm computing now effective potential here. And then we have dx, G1, dx, 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 plus dot, 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 okay? Some contraction, doesn't matter. In the nodes, you have the exact contractions. Now you see the kinetic term has 2 derivatives, okay, which translate into a power of 1 over r squared, right? And there is no Ls here in this operator. It has the correct units, and this is simply this loop diagram, no? The vacuum loop at finite volume. And there are some factors of pi that count the number of degrees of freedom. So it's pi, I'm not sure I wrote it, I think, well, it should be d minus 2, okay? The number of degrees of freedom, okay? But now you see, then we can write r to the 4, which is going to come from a 2-loop diagram with the terms that appear here, okay? Okay, so roughly is dx dx some operator like so, okay? And I'm going to give you the coefficient in a second, but let me put now simply a c, a constant, Ls squared, and then we'll have R6, C, Ls 4, and then finally, so this will come from 3 loops, so we can write a 3-loop diagram like this, plus this, okay? And then finally, we'll get something proportional to G1, okay, which comes with R to the 8, okay, and some calculable CDE, some calculable coefficient here, okay, and similarly for G2. Now, this whole expansion can be actually summarized with this equation. So let me write the vacuum energy. The vacuum energy is precisely equal to R squared minus pi over 3 d minus 2 plus some calculable coefficient over r to the 7 plus order of 1 over r to the 9, okay? And this d delta it's equal to, it's linear, so let me write it like this. Alpha G1 plus beta G2 with some calculable alpha and beta that I'm not going to write now, okay? So the point I'm trying to make here is that the leading corrections to this to the potential energy between this QQ bar pair comes from effects which are 1 over r to the 7. Okay, the rest is fixed by the symmetry breaking pattern. Okay, and now what we would like to do is to bound these coefficients. Okay, these coefficients, by the way, can be and have been measured in the lattice. Okay, in the recent years. Okay, and now we're going to use the S matrix to bound these coefficients. Which S matrix? It's going to be the S matrix for the scattering of the Goldstone bosons. Okay? So now So what I can say a few words of what I'm going to do next, but what can I write? Let me see if I can write some equation. Maybe I can mention an example, and tomorrow I'll cover it in more detail. But what I want to say is that, for instance, for d equal 3, okay, just plug d equal 3 on, this, on the action. D equal 3, I mean, this is the number of flavors, okay? So it means one Goldstone, d equal 3, okay? Remember that we are in 2 dimensions, and we have d minus 2 fields, okay? So for d equal 3, it cannot be more simple, because we're in a system that roughly looks like this. We have one Goldstone, okay? So in particular, these equations apply, because now we have one Goldstone scattering in a line, which is nothing but like 4-dimensional forward limit, right? So all what I did here will apply to that system, okay? So we can, but except that now we have some EFT with some definite predictions for all these coefficients that appear on here, okay? So you can compute this amplitude. So I'm computing now the scattering of these Goldstones, which already has dx of some variable, okay? So it's simply an AFT of Goldstones, the kinetic term plus higher derivative terms predicted by this action, okay? And now the amplitude depends only on Mandelstam variable S, because we are in a line, okay? And the amplitude looks like so. There is a C2 S square plus some loop correction, C2 square over times S cube over 4, plus 2 gamma 3 minus C2 cube over 24 S to the 4 plus dot, dot, dot. Now I'm going a bit fast, but I would like just to introduce the problem, and tomorrow I'll do this slightly more careful, okay? But here the message is that there's a Goldstone amplitude. There are loop corrections. Here there's an accident where loop corrections do not give logs, but they give i's, okay? And the accident is because this term here comes from S cube times log S, okay? There's a log. But the crossing symmetry in this case is very simple, because it's S2 minus S, because there is no T. And it gives you S cube of log of minus S. And now you can factor out the S cube here. You have log of S minus log of minus S, which is simply the argument of the log, which gives this I, okay? It gives you, so this will give you S cube I pi, right? And then there's a 1 over pi factor from the loop, which cancels the pi and leaves only this I, okay? So this is this diagram here, okay? And then we have this diagram here, which is 3 loops. That gives you this S2 cube, sorry, 2 loops, and it gives you this C2 cube. And then there is this gamma 3, and this gamma 3 is again G1 and G2, a linear combination of G1 and G2, okay? But now the point is that if we evaluate the arc, we can compute now this arc integral. What we will get is we'll get an equation that looks like this. We'll get C2 square over S naught. I'm not putting now factors. I'm skipping. There are some numerical factors, okay? And to follow that notation here, I should put an S here, not S naught. Plus, let me see if I have it. Plus this, plus 2 gamma 3 minus C2 cube, okay, there's some factor, 24, plus order S, okay? Okay, so this will be some calculation, okay, of a leading, of an arc, okay? So this will be A, in that notation is A4, okay? A4, okay? So here, it's a bit fast what I explain now, but I'm trying to draw an analogy where in this system, okay, the system holds an S matrix for which I can write similar dispersion relation as the one here, okay? And we see that if we want to bound the leading non-universal operators, okay, via this dispersion relation, we get some contamination from IR loops, okay, that screen any possible bound on gamma 3, okay? Gamma 3 or G1, so this is a function of G1, G2, okay? It's just the EF2 operator, okay? So what I would like to show next is how can we actually get a sharp bound on gamma 3, and then how these ideas generalize to higher dimensions, okay? Let's say other systems that are in higher dimensions, okay? And I think I'm well over time, so tomorrow I'll continue from here, but I will make some further remarks about the logic, okay? I'll leave it here, thank you.